In section 4.3, we're going to be recognizing the shapes of basic polynomial functions, describing the graphs of polynomial functions, working with continuity and behavior, intercepts, local extrema, and points of inflection. We're also going to be identifying complete graphs of polynomial functions by using the other objectives. So first of all, let's talk about the basic shapes of polynomials, and we're going to work on the ones of odd degree. So an example of one of odd degree would be something like y equals 3x to the fifth. Okay, so by odd degree, I mean that 5 there. So that could be to the third power, so it could be a cubic, it could be to the 7th power. So if we have a polynomial of odd degree and a is greater than 0, then it's going to be, so a is this value here. If a is greater than 0, then the shape of the graph is going to look sort of like this. And in addition to that, if a is less than 0, then the shape of my graph is going to look more like this. Okay, so you can think of the a very much like you think of the slope to a linear equation, and that is, if a is greater than 0, then we're going to be rising from left to right, whereas if a is less than 0, then we are going to be going down from as you move from left to right. All right, so that's odd degree, and now let's go ahead and talk about our even degree. So this time we're talking about even degree, so an example here would be y equals 3x to the 4th power. This again is your a value, and this is degree when we say even degree. If a is greater than 0, then the shape of my graph is, or the graph is going to open up. Okay, now what we don't know is, depending on that degree, it's what's happening in here, but we do know that it opens up, so both should be going the same direction, and that is going up. All right, and then when a is less than 0, so for example that a is a -3 instead of a +3, what happens is that the shape of this is going to open down. Now again, we don't really know what happens in this area, but we do know that it opens down because a is negative. For every graph of a polynomial function, it's going to be continuous. It's going to be an unbroken curve with no gaps, no jumps, or no holes. So we're going to look at several different graphs here, and then we're going to talk about which one is, which ones are and which ones are not polynomials. So let's say I have something like this, or like this. Okay, so each of these. So keep in mind, polynomial function is going to be continuous. This first example is not, because of the hole in the graph. That is not a polynomial function. The second one, you've got these sharp turns here and here, so this one is also not a polynomial function. The third graph that I have, this one is. There are no there are no gaps, there are no jumps, there are no holes, there are no sharp turns on this one. So the third one is an example of a polynomial function, and the last one is not, because of the hole that we have in here. Okay, so those are some examples. And now we're going to talk about end behavior. So first of all, when the absolute value of x is large, the graph is going to closely resemble the graph of the highest degree term, and this will make more sense in the next example I give you. In addition to that, when a polynomial has odd degree, then one end is going to shoot upward while the other end is going to shoot downward. So we're going to look something like this. And then if it's even degree, you're either going to go both down or both up. Okay, sort of like a parabola. Now what you don't know, where you don't know what's happening is in this area here. Okay, those can't be determined by just simply looking at the degree of the polynomial. Now here are a couple of examples, and I already have graphs for you. So in the first example, I have this polynomial and its graph, and then this and its graph. So you notice what I've done is I've actually taken this and graphed just here. And what I want you to do is notice the end behavior and what's happening here. So first of all, we have degree 3 in both of these. So since it's degree 3, you notice that one end is shooting upward and the other end is shooting downward, and that happens on both of them. Now, the other thing I want you to notice is that the end behavior of f of x in this case is going to be very much like the end behavior of g of x, even though they're not the same functions. What's changing and what's different between the two is what's happening in between here. So to get an idea, the reason this is useful is to get an idea of what a function like f of x looks like is you might just want to graph the term 0.4x cubed, and that will give you an idea of what your graph's going to look like. And then in number 2, we have both graphs once again. So we have this function, and here's its graph, and then here. Okay. Now in this case, you notice that we have degree 6. Okay, so degree 6. Now this time it's going to be an odd. I'm sorry, it's going to be an even function. So both of them are opening downwards in this case, and they're both opening downward because this right here, this a value that we talked about, is negative. So again, both are opening down. And the area that we can't determine from just looking at that leading term is what's happening in here. Okay. Now if we look at the a and this guy here, the a up here was 0.4. With that a being 0.4, the a is greater than 0, so you notice that you're rising from left to right, so that we know the general shape of the graph is going to be this, whereas the general shape with the a equal to the -3 is going to be that it opens downward, so both pieces are going to open. And then we have something going on in here, but we're not exactly sure what that is yet. And now for the intercepts of the graph. If you have a polynomial with degree n, then it has exactly one y-intercept, which is going to be equal to the constant term. Okay, so we need to know what the constant term is, and we'll look at an example to help us with that. And it's going to have at most n x-intercepts. Okay, so let's say that I have a polynomial, and it's polynomial. Okay, if I have this, then the first thing is that the y-intercept is going to be equal to the constant term. My constant term is this guy here. All right, so that is my y-intercept. So it's going to have a y-intercept of 5. And in addition to that, we are going to know that it has at most n x-intercepts. So that is going to be the degree of the polynomial. So now keep in mind that this is at most 3 intercepts. It does not have to have 3 x-intercepts. All right, and now for the multiplicity of the graphs. So when you're talking about multiplicity, you're talking about the zeros. So if C is a 0 with multiplicity k, so what that means is that 0, remember, that's the same thing as a solution. So let's say 5 is a solution with a multiplicity of 2. Then that polynomial, so we are interchanging these c's and k's here instead of using numbers. So if k is odd, then the graph is going to cross the x-axis at c. If k is even, the graph touches, but it does not cross the x-axis. And this is going to be much easier to understand when you're looking at an actual example. So let's see, let's work through this example that I have here. You've got your f of x. So f of x, it's written in factored form now. So that means that it's going to be very easy to find the solutions. Okay, so my solutions are going to be -1, +1, and +3. Okay, and I get those by solving each one of these. Those are my solutions. Now what we're going to talk about is the multiplicity of each one. Now you can tell the multiplicity by looking at the exponents here. So -1 has a multiplicity of 3. 1 has a multiplicity of 1. And 3 has a multiplicity of 2. Now using that, we can tell whether it's going to touch the x-axis, or whether it's going to cross it. So what happens at each one? Because the multiplicity is 3 for the -1, it's odd. That means that it's actually going to cross the x-axis. Okay, and then for 1, again, the multiplicity is odd. It's 1. So again, it's going to cross the x-axis. And then at 3, it is going to touch the x-axis because it is even. So the difference between crossing and touching is actually, let's say, if I have, okay, here is an example right here of where it crosses the x-axis. If I were to show you an example of where it touches the x-axis, then that would be like this. Okay, there we have a touch. Okay, so you have the difference between a cross and a touch. So we could use the information that we found here to come up with a graph for this. So let's say, what do we know so far? We know at -1, it's actually going to cross it. So let's say that's -1, and it's going to cross it there. And then it's going to cross it again at +1. And then it's going to touch it at 3, which is down here. So that means that our graph might look something like this. Okay? And if you look at that, let's look for a second on our calculator and see what that one actually looks like. Okay, so here we go. A little bit like what I just said. I think I have more than one graph here, so let me go over and turn these off. Okay, so there we have an example. Not a great graph, but if we made some adjustments to that, made that maybe -7. And my board's not responding to me changing this, so we might have to leave it here. But anyway, so if we go back to this graph, then you realize that what we know so far, we've used everything that we've found out about the multiplicity and the end behavior to come up with a graph that is a pretty good representation of this f of x that I have. All right, and now we're going to talk about local extrema, local maximum, local minimum, and these are things that we've already covered. So if you have a polynomial function that has degree n, then it's going to have at most n minus 1 local extremas. So, and then the points of inflection are kind of going to go alongside that, and they're always going to be less than the number of local extrema. So, for example, on this one, let's say that I have something, that I have this function, and this is one we've already used. Okay, so if I have this one, then what do we know about it? Its degree is going to be 6. So since its degree is 6, then what that means is it's going to have at most 6 minus 1 local extrema. 5, and that's at most. Okay, and then in addition to that, it's going to have, since it's degree 6, it's going to have at most 4 points of inflection. Okay, so in this case, if you graph this, then you realize, and we have graphed it previously, we looked at a graph, it looks something like this, okay? So your local extrema are these guys. And so it actually ends up having 3, but that's okay. The 5 is the number that it can have at most. So it has 3 actual. And then when you look at the point of inflections, well, your point of inflections are going to occur there and there. So it's going to have 2 of those, which is, like I said, 1 less than the number of local extrema. So you can use your degree to find the maximum number of local extrema and the maximum number of points of inflection. But you would actually have to go further to find exactly what's happening there. Okay, so this concludes what I have for section 4.3. What you should be able to do from this section is use the information that we have talked about to find complete graphs. So, for example, let's say that you graph a function that is a 4th degree polynomial. It has an x to the 4th in it. And on your calculator, you see something like this. Okay? You should be able to use what you know from this section to say, okay, that is not a complete graph. Actually, your calculator wouldn't give you the arrows, so it would look more like this. Because this is a 4th degree polynomial and this is positive, then we know that either both ends are going to open up or both ends would shoot down because it's an even degree. In this case, your a value is 1, which is positive, so both ends would open up. So what you should be expecting then is to extend your graph because you know this is probably going to need to go back up. Okay, so the blue part would be the piece that you're missing there. And that's how I would expect you to use this information from section 4.3.